Hi, comma. This is one of the more difficult sections of related rates of this chapter. So we'll be going over these. They're pretty important stuff. How the rates are going to be related. That's what it's called, related rates. So let's look at some rates right here and see what rates are. Can someone give me examples of rates? Um, or think of some rates? First of all, the easiest one would be 20 miles per hour. Or you can say 10 uh, degrees per minute. It's going up positive 10 degrees per minute. Or if you're a house builder, you're going to build, let's say, 120 houses, HOUSES, houses per year. So you build 120 houses per year. It goes up 10 degrees per minute, or you can go down 10 degrees per minute, or you can also go 20 miles per hour. That's MPH, right? So what is the common denominator of all these three expressions? Well, this could be written as 20 miles per hour. So the common denominator is always in terms of time. So every time you have division by time, you have a rate. That's what they call rates. So let's look at some examples. Before we do that though, I'm going to give you some notations that you're going to need. Usually R is reserved for radius. H is going to be height. D for diameter. A is for, it's not apple, it's not kindergarten. A is for area. And what is V? V is usually reserved for volume. We'll also reserve theta as degrees or radians, or degrees in radians, okay? So if I take the derivative with respect to time of V, what do I get? It's very simple. I just put the V on top right there, end up with dV dt, the instantaneous change of volume with respect to the instantaneous change in time. So dV dt. What's the derivative with respect to time? So time is of the essence. Time is the most important thing. Of h cubed, well, the derivative of h cubed using the power rule, bring the power down, subtract 1 times, and then the derivative of that is going to be dh dt. How the height is changing with respect to the change in time. Okay, so let's do some problem. I'm going to just do one example for you. It's a real simple one, and then we will. And each question is a little bit tricky, so you're going to have to do lots of algebraic manipulations on these. Okay, so let's look at example number 1 on page 241. Air is being pumped into a spherical balloon. Here's a spherical balloon. Air is being pumped in. So the volume increases at a rate of 100 cubic centimeters per second. So the volume is increasing at 100 cubic centimeters per second. So air is being pumped in here. What is this? What do you think that's called? That's dV dt. The change in volume with respect to time is going to be positive 100. Of course, it's going to be cubic centimeters per second. How fast is the radius of the balloon increasing? So what are we looking for? How fast is the radius increasing? So you're looking for dr dt. What's that? The change in radius with respect to time. That's what we're looking for. Okay. When the diameter is equal to 50 centimeters. Or since everything is in radius, the radius is going to be at radius equal to 25 centimeters. Okay. So The important thing is we need some function that we need to take the derivative of. We do know the volume formula. The volume of any cylinder is going to be 4/3 pi r cubed. And what do you think we're going to do with this? We're going to take the derivative with respect to time on the left side as well as the right side. On the left side, you end up with a very simple statement, dv dt, right? The dv goes on top. The change in volume with respect to time. We're going to factor out 4/3 pi, and we're going to take the derivative with respect to time of r cubed. We already know how to do this. We did this just a little bit earlier. That's going to be using the power rule, 3r squared times the derivative of this, which is dr dt. Also multiplied by 4 pi over 3. The 3 is going to cancel out with that 3 as well. So dv dt is equal to 4 pi r squared times dr dt. We already have, at this stage, after you take the derivative of this volume of cylinder function, not cylinder, excuse me, sphere function, you're going to plug in r in here, which is 25. The diameter was 50, so the radius is 25. You're also going to plug in dv dt as 100 in here as well. And dr dt is what we're looking for, right? So just plug in along as you go. That's it. dv dt is 100. It's equal to 4 times pi times r, which is 25, times 25 times dr dt. 25 times 4 is 100. So it's going to be 4 times pi times 25 times 25. At this stage, I'm just going to cancel out 25 times 4 is 100. That cancels with that 100. You end up with 1 over 25 pi as dr dt. So dr over dt, 1 over 25 pi. That's your exact answer. The unit is going to be, the radius is changing in centimeters per time. Our time was seconds. So centimeters per second. Let me just verify that. Yeah, 1 over 25 pi, which is approximately 0.127 centimeters per second. Example number 2, 3, 4, other type of examples I'm going to be doing separately because each example has different techniques and keys that you're going to use to try to solve these problems out. Good luck on related race.